Hello, guys. Good afternoon or good evening, wherever you are. It's Samuel here again. Jack Samfrimpon. I think I've finally settled on a name for my YouTube. I've been switching. I think if you've noticed, I've been switching the name for quite some time now. But I think this is pretty much the name I use for all my socials. So I just decided to, go with it. Yeah, the last time we met, we talked about some algorithm that we can use to find substrings of a string. And using that, we can find which of those substrings are palindromes. And using that, we can find which of those palindromes are above or equal to a certain length, right? That particular algorithm was called sliding window. So we use the sliding window to go through the the string to get the substrings and do all that calculation. If you haven't watched that video, please go and watch it and like it. Today we'll be looking at another issue. It's also about strings. I think if you really want to be good with these kind of questions, you have to tackle them from different angles. So this is a bit different. It's not the same kind of question. So let's see. Maximum number of non-overlapping palindrome substrings. So it's kind of a lot of conditions here. Is the maximum number of non-overlapping palindrome substrings. So this is the question. You are given a string S and a positive integer K. So the keywords are the string has been given a positive integer k2 has been given. Good. Select a set of non-overlapping substrings the sorry from the string S that satisfy the following conditions. The length of each substring is at least k. Each substring is a palindrome. Then return the maximum number of substrings in an optimal selection. A substring is a contiguous sequence of characters within a string. All right, so here this is what is happening. We've been given a string. It could be anything. Let me type here. Abracadabra. I think today I spelled it right. So we've been given a string abracadabra, right? Good. And then a positive integer k. So let's say a positive integer k. So let's say k is 2. S is abracadabra. All right. Good. Well, now, what are we supposed to do? You are supposed to select a set of non-overlapping substrings from the string S that satisfy the following conditions. The length of each substring is at least k. Each substring is a palindrome. So this is a lot of conditions in this question. So let's see some of the examples. So they say if an input A, B, B, A, C, C, D, B, B, D is given and K is 3, the output will be 2. Let's see how they got that. All right. Let's see how they got that. So is this K was what? 3, right? Cool. That means the substrings which are palindromes, we can have A, B, A, right? We can have D, BBD, we can have BB and all that. But K is 3. So since K is 3, we want the substrings which are palindromes and also are greater or equal to 3. The length of that substring is greater or equal to 3. So that will be ABA then DBBD. So first of all, let me explain how I tried solving this question the initial time. I tried using the the sliding window to go through it. It's good in some sense. It will first of all give you the all the substrings in that particular string. You can use some calculations to get those substrings which are palindromes, and among those which are beyond their length is beyond a particular length, right? But the issue here is I think the main issue here is how to get the non-overlapping substrings. It's very difficult. You have to imagine a lot of things. So upon the fact that I couldn't solve it using the sliding window, I read into it, and they were talking about other forms of ways you can solve it. One of them is expanding around the center and dynamic programming and all that. But I think the expanding around the center was a bit intuitive to me because I think as human beings we already know it, but we just don't put a name to it. We already know it, right? So let me show you. If you see a word like ABA, you already know it's a palindrome. But how do you know it's a palindrome? You just kind of know it, but in a programmable term, we say that when you expand around the center B, the elements on the right of B, as and when you keep expanding to the right and left, they will all be the same, right? So let me give you an example. Let's say Abiba, right? That's not how we spell Abiba, but let's just say Abiba. I intuitively know it's a palindrome. Nobody needs to tell me that. But to program it to prove that this is a palindrome, I will take the space between the two e's as my center. So that would be my pivot. And as and when I'm expanding outward, all the elements on the right and left at each length that I'm expanding outward, they will be the same. So when I expand one element outward, that will be E, E. So E to the left, E to the right are the same. When I expand two lengths outward, the elements there will be B and B. So B to the left, B to the right are the same. The same thing for three outward. So we kind of know this in our subconscious, but we've not really taken time to formalize what is really going on in our mind that makes us know this. So that was the way the expanding around the center when I read about it. That was what I understood about it. And today we are going to learn the algorithm to use to solve this particular issue. Another thing that I learned to it took me way back into school. It's called scheduling, right? Operating systems. Mr. Comey. Hello. So yeah, this is where your operating systems come in, right? So let's say you have some events that you want to schedule on a timetable. Okay. You have some events that you want to schedule on a timetable, but you want to schedule the maximum number of events. Some of them are overlapping, right? But you don't want to have an overlapping event in a classroom. You want to schedule some events within a classroom block that they wouldn't be overlapping, and also you can have the maximum number of events. So let's say Maths 151 start at 8 a.m. all the way to 10 a.m., right? What else? Math lab starts at, it's supposed to, let's say the lecturer submitted me, I want 9 a.m. to 11 a.m., right? What else? Basic mech starts at 12, ends at 14. And then, what else? Autotronics. Is that how it's spelled, autotronics? I don't know. Starts at 11, ends at let's say because it's a very long session, different batches. Let's say it ends at 16, 11 a.m. to 4 p.m. All right. Now you need to schedule this such that you can have the maximum number of classes running. How do you schedule this? First of all, you schedule by arranging them in a way that the ones that finish, should I say finish, the ones that complete the earliest comes first. So among these courses, which one completes earliest, like the course, right? The period. Which one is the earliest to complete? That will be Math 151. It comes first. Then the next one should not overlap with this, but it should also be the one to complete the earliest among these, right? So the next one, 9, will overlap with Math 15. Math lab will overlap with Math 151, so we wouldn't take it there. But the next one, which will not overlap with Math 151, but will complete the earliest, will be Basic Mech, right? So we bring Basic Mech here. So this is what we have. Okay. So we have Math 151 and Basic Mech. So now if we schedule our timetable for the classroom in this way, that means Math 151 will start from 8 to 10, Basic Mech will start from 12 to 2, and there will be even another space for another 2 period or 3 period class that we can push here, right? So we can have the maximum number of classes using this technique. All right, so let's start coding something. Um, how many conditions are we looking at? Okay, let's see. First of all, the substring, the length of the substring is supposed to be greater or equal to the key. Okay, the substring is supposed to be a palindrome. Okay, what else? So the substrings, they are supposed to not overlap, non-overlapping. And what else? Okay, so I think that's pretty much it. Okay, that's pretty much it. These are just ways to guide me to know what I'm doing. So let's use the expanding around the center to first of all get the substrings. Then when we get the substrings, we'll use other techniques to satisfy the other conditions that we've been given. All right. Okay. So let's start. How do we start? Okay. So for I in the range of the length of the string, so we are going to loop through the whole thing, right? So this is an arbitrary. I'm going to have an arbitrary this thing over here, an arbitrary function here. I'll actually implement it, but I'm just putting it here. So expand around. So expand around the string I expand around this string I I plus 1. Now, why are we doing expanding around a string I and expanding around a string I plus 1? So let me explain. All right. When we take when we take the word ada, which is uh, which is a palindrome, we have to slide through from A to D to A. Then we use each one as a center to expand around. All right. So for A, we can expand around A. If we expand around A, our first element to the right and left, to the right is D, to the left is not existent, so we won't even bother. When we go to D, we can expand to the right and left. So when you expand to the right, you have A. When you expand to the left, you have A. So we can get something. But look at a word like Ada with a double A, right? So we have to find a way of, this is an even number of, the string is an even number, this string is an odd number. So for odd numbers, you can easily center our pivot on an actual element. But for even numbers, since we can center our pivot on an actual element, it has to be within two different elements. So this is what I'm trying to explain. If we take if we take I, right, for I in S in Ada, for I in Ada, this is pseudo code, right? I. Oh, this is what I'm trying to explain. I. That means we have A and A. So it's still A, and you are trying to expand around A. But that means you are expanding around an element. So you are using the approach to expand for odd numbers. I mean, for odd strings. All right. You are expanding around an actual element. So one element will be in the middle and you expand around it. So at the end of the day, it will be an odd, if you get a palindrome, it will be an odd palindrome. But if we do but we also know that palindromes are not just odd, they can be odd or even. So if we do I plus 1, this is what happens. Let's say we have A and we also have D. So in this scenario, our pivot is not on A and it's not on D, it's in the space between A and D, right? So we have an even number of, at any point in time, we have an even number of strings in our substring and we can expand around. So with this, we can get to, we can have our I as D, right? And our I plus 1 will also be D. So in this situation, we will have DD and we can expand around it. And we will have ADDA as a palindrome. So it's just a way of handling there's a situation where your palindrome is odd or even. All right. Okay, back to the question. So we can expand around we can expand around I plus 1. Okay. This is pretty much what we are going to do. So let's implement the expander around. It takes in the string, it takes in the I will be my left, the element on my left, and then I or I plus 1 will be my element on the right. Okay. So how do we expand around? Uh, Expanding around to, you need to start from where those particular elements have been giving you, the left and the right. Then you always add one, go and try and expand like on both sides. So let's look at it. So we can use a while loop. So while your left hand side is always greater than 0, so that we don't go into the negatives and have an indentation error or index error, right? And your right is less than the length of S. All right, that one too, you don't go outside of, just to make sure you don't go outside of the string. So let me just do it in such a way that we'll get the substrings first. So print S L, right, R plus 1. Then L, because we will keep on reducing our left, L equals L minus 1, R equals R plus 1. Let's follow what I'm doing over here because this is pretty some way. So over here, we are just trying to get our substrings. We don't care if they are palindromes or not. So we see we have A is a substring, right? AB is a substring, B is a substring, AB is a substring, BA is a substring. It goes on and on and on and on and on, right? Good. Now we can have substrings which are palindromes. So let's focus on the substrings which are palindromes and forget about the other substrings. So in order to ensure that the substrings are palindrome, as and when you are expanding outside of the pivot, the string on the left, right, should be equal to the string on the right. Okay, so let's run this and see. The string on the left should be equal to on the string on the right. So you see we have a ideally, not ideally, technically, a single string is a palindrome because when you mirror it, it's still a single string, right? Then we have B, then we have AB, then we have CC, okay, then we have D. So you see, we've only gotten our palindromes. Now, there is a condition that the length of the string should be greater or equal to K, okay? The length of the string should be greater or equal to K. Now, when we bring that condition here, it might break the loop, right? What if we needed to expand two more times to get uh, the substring, which is a palindrome, and satisfies that condition? If we just bring it right here in this while loop condition, it might break the loop. So I want to check for it inside the while loop, not right on the while loop. Okay. So let's check for it. So if how do we make sure that the length of the substring is greater or equal to the key? So we take the index on the right, subtract the index on the left from it, add one to it, right? If you have numbers 1, 2, 3, and you want to know how many numbers you have, 3 minus 1 is 2, plus 1 is 3, right? If you have 11, 12, 15, it's three numbers. But if you do 15, 11, 12, 13, it's three numbers. But if you do 13 minus 11, you have 2. So you have to add 1 to it to get the actual this thing. I hope you get it. So R minus L plus 1 is greater or equal to K. If R minus L plus 1 is greater or equal to K, then this is what you are going to do. You found your guys. All right. So that this we don't move the L plus 1, R plus 1, L minus 1 into the if, because for the L minus 1, R plus 1, we always do it regardless of the condition. So if it's greater than or equal to K, we note it down. Okay. Now how do we tell if we've been able to tell their palindromes they are greater or equal to K? How do we tell if they are non-overlapping? For they to be non-overlapping, we always need to select the earliest first, the one that completes the earliest first. And how do we select the one that completes the earliest first? You remember they said the length of the substring is supposed to be K, right? Or more. So if it is a palindrome and it satisfies this condition, then we can stop right here. The moment we find one, we can stop right here, not like continue searching for more. Because if we search, so if we find something like, let me give you an example. This is this. So A D D D D D A, right? This is a substring. This is a palindromic substring, right? Now, if we find DD, let me do it ADD. If we find just DD, we don't need to go ahead and get the full ADDA. Let's say K is 2. Okay, I had to tell you that K is 2, S is ADDA. If we find DD, we don't need to try and go all the way to like find the full string, because it will still satisfy the same condition. So we can just stop right here. When we find 110 within the, when we are doing the expansion, we find the first one that satisfies for the I that we are currently working on. We can just stop right there. So let's implement that here, right? So we can just return. Okay, you can just return. So let's look at the what we had. It is expecting 2, and we printed what? ABA and DBBD. They are just 2, right? Over here, it's not expecting anything. It didn't print out anything on standard output. Over here, it's expecting 4. We had 1, 2, 3, 4, 5, 6. Okay. Over here, it is expecting what? 5. Over here, expecting 2. We have 2. Over here, it's expecting 10. And I don't think we have 10. Or do we have 10? 1, 2, 3, 1, 2, 3, 1, 2, 3, 1. Okay. So over here, it's expecting 4. We had 6. That's fine. So there is also a condition to check if they are non-overlapping, right? First of all, we've been able to get the substrings which will finish the earliest, but we still need to check like if they are really non-overlapping. So how do we ensure that? We can ensure that by having our global variable which will help us check that. Okay. So we can have a global variable called last end, and it will be equal to -1. Why is it equal to -1? Because we don't want it to be an actual number where the first element we will check wouldn't satisfy for that condition. Okay. So this is what we are going to use this last end for. For it not to be overlapping truly, the R, the element on the right of what we are currently evaluating, right? It should be greater than this last end. The L2 should be greater than this last end. Okay. So this is what it's going to be like. This is wild. So and R, right? L is greater than last end. Okay. So if L is greater than last end, last end equals what? R. Okay. So our L should be greater than the last end. And when that is true, we are supposed to set our R to the new last end so that we can continue checking. All right. It has some syntax error. So let me see. One, two. Okay, we can bring this here. One, two. Then what else? Why is it giving me this error? Oh, it says local. Okay. Okay, cool. So I can have global last end. Okay. What's this? Uh, come on. Can I hide this? What's the error? Expand around. Last end is not defined. The last end is here. Oh. I'm coming. Def init self. Let me just do it like this. Self dot last end is -1. Self dot last end. Right. Self dot last end. So let me see. Okay. So this one was the one failing. Now I have just four. All right, cool. So self dot found palindromes is an empty this thing. Then this has been a very long session, honestly. It's this question really blew my mind. But yeah. So when we set our last end, we can add our found palindromes. Dot append LR. Okay. So I'll just print I for I self dot found palindromes, but it won't just be I. It will be I0 all the way to I1. Si0, right? All the way to no Si0 all the way to Si1 plus 1. Okay. So let me see. So I'm just trying to print the values that I found just to be sure. Okay. Then I can return the length of self dot found palindromes. All right. Okay. So that's pretty much it. So this is what I've been doing all this while. That I think I've already confused some of you guys, but let me explain. We look through the string given us, right, from the first character to the last character, but we are just interested in the index. Okay, so let me give you an example. I'll still use Abiba. So this is our first iteration. So iteration one, we have A, right? And then that's our character. The index is 0. Okay, so if you check the code, what is it trying to do? It's trying to expand around the 0, 0 and then 0, 1. Okay, so this is it. You are expanding around 0, 0, which is A, 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 which is still A, right? And then 0, 1, which is A, B, okay, which is still AB, right? So you see over here we are expanding around a character. Over here we are expanding around the space in between two characters. So we have two characters as our beginning whatever to expand around. Over here we have just one character as what we are expanding around. So when we try expanding around the first A, we can't go further because of like the this is the first guy. When you're expanding around A, B, that one too, we can't go further because it's the first guy. So let's say our K is 2. Okay, our K is 2. None of these will satisfy. This is a palindrome, it's a substring, but it's not 2 or more, so it won't satisfy. This will not also satisfy, so we just forget about it. So let's say on our second iteration, our I is what our I will be 1, okay, because it will be B and B is 1. Okay. Now our I will be 1, 1, which is still B. So we'll be expanding around B. Our I plus 1 will be 1, 2, okay, which is BE. We'll be expanding around B. So we can continue expanding around B. We'll have A, B, E. If we expand around B, on our first expansion around B, we'll have A, B, E. We can expand further. If we expand around BE, on our first expansion around BE, we have A, B, B, A, B, E, E. But we can't expand further because we can't go beyond A. On our third iteration, okay, our letter will be E, and E is 2. Okay, so our I will be 2, 2. Our I plus 1 will be 2, 3. This is all the expansion algorithm. Okay, so 2, 2 will give us E, and if we expand around E, we'll have BE, B, E, E, sorry, BEE. We also have A, B, E, E, B. None of them is a proper palindrome. None of them will satisfy our conditions. But we can also have, in that same iteration, we can have 2, 3, which is 0, 1, 2, which is EE. Now, if we expand around EE, EE is still there, right? We can have EE, BEEB, ABEEBA. But as long as we have EE, it's a palindrome, it's a substring, it satisfies the length 2. We don't even need to continue with this. We can just quit here and then return it, right? So that's pretty much the implementation we've done here. Let's submit and see. All right, so apparently the algorithm beats 31% of submissions for the runtime, and also 31% in memory space usage. Okay, that's good enough, but we can improve it more. This has been really a very long session. I spent some time to understand this problem. It's not that easy. It's strings. Usually strings are supposed to be easy, but this is crazy. So yeah, guys, let me know what you think about the problem and how we can improve the time and space complexity. All right. Thank you very much and see you later.